is going to go over Chapter 3, Systems of Linear Equations. We're kind of bouncing back a little bit on what we've been learning. In this video, we're going to decide whether an ordered pair is a solution of a linear system. We're going to solve the systems by graphing, and I'm going to give you some tips on using Desmos.com instead of the by hand graphing method. We're going to solve the linear systems by substitution, elimination, and look at some special systems. When we're solving a system of linear equations, the solution is where the two lines intersect at that specific x value and that specific y value. So if you look here, they intersect directly here. It looks like probably around the x value of 9. So that would be 2009. And it looks like around maybe 35 to 38. So the first thing is, how can we decide if an ordered pair is a solution, and why is that still important? Because we always want to be able to check our work. So the solution set of a linear system of equations is an ordered pair that satisfies all of the equations in the system. So when I plug in the ordered pair, I have to do it to every equation in the system. So if I'm looking at this system of equations and then this point, I want to replace x with -4 and y with 2 in both equations. And when I replace, I'm going to use parentheses because when I'm using those parentheses, it'll make the arithmetic more clear. So when I'm entering this into the Web 2.0 calculator, I'm going to enter it just as that, and I'm going to get that -6 equals -6. So when you're calculating in the calculator, you're only looking at the left-hand side, and you get a true statement. So a true statement means that it is a solution. So I have to plug into the second equation before I'm sure that it's a solution to the entire system. And I get another true statement, which tells me that that point makes both true, so it is a solution of the system. If I want to decide whether a given ordered pair is a solution, again, I'm going to replace x and y with those values, and I'm checking to see if it's true. So in the first equation, I do get true when I plug it in. And the second equation, I get false. So what does that mean? If it's false in any one of the two equations, it is not a solution of the system. If I want to solve by graphing, I'm going to deviate a little bit here from the PowerPoint. When you're graphing a system of equations, I want you to open Desmos.com and I want you to type both equations directly into Desmos. You do not need to solve them for y. You can type them in exactly as they are, and then you can zoom out or zoom in using the menu on the right-hand side. And if you put your cursor over the intersection, it'll give you that actual value. So then we're pulling it over to the lab. So the lab is going to be a little more picky about those. So when I'm in Desmos.com and I'm graphing, I will take the x and the y intercept, and I will plug those in to the MyMathLab graphing systems. For some reason, the whole number x and y intercepts, it does make it easier to graph a line. If the x and the y intercepts are not a whole number, like right here, then I would look on Desmos for where the line actually crosses two corners in the grid, and I would plot those 2 points and use that line tool to connect them. So I could check the solution to the equation by plugging in both of those. Now, when I'm graphing a system of equations, I have 3 possible outcomes. The first outcome is that they cross 1 point, so they have one solution. They're parallel lines, so they have no solutions. Or the lines are multiples of one another, so they're graphed one on top of another. And in that case, every number is a solution. If there's a number on one line, there's a number on another. So there's an infinite number of solutions. So when I'm solving via substitution, and we're going to circle back to those line examples, if I'm solving via substitution, I'm solving one equation for a variable and plugging it into the other equation. So if I want to solve this system, I'm going to work smarter and not harder. The bottom equation is already solved for x. So I'm going to replace x in the top equation with what it's solved for. So this gives me all y values, which means I can solve as a normal equation to get my y value. Once I have my y value, I can plug into either the top or the bottom equation to find my x value. I would plug in the bottom one because it's already solved for x, so you get x equals 0, which means the point 0, 2 is a solution. So if I were to put this in a series of steps and explain it, the first step would be solve one of the equations for either variable. Then you would substitute for that variable into the other equation, and you would solve. Last, you would find the other value by replacing the variable with the number you found. Then you would ideally want to check the solution. So when you're in the lab and when you're taking your test, it's always a positive to check that solution. So if I wanted to solve this system, the question becomes, if I really want to use substitution, which one should I solve for the variable? I would solve equation 1 because there's no coefficient, so I don't have to do any division. Then I would replace that y with what the y stands for. I would solve it up for x and I get 2. I'm going to plug that 2 into any one of the equations. Since I already solved the other one for y, it makes sense to plug it in there. And so I get the point 2 comma negative 3. Now this is one I wanted to briefly talk about, because we do see this in the lab where we have fractions. As I've said throughout the course, fractions are challenging. So what we can do is we can multiply this equation by a value that gets rid of all the fractions. So if you look at 2, 4, and 2, the least common multiple of all three of those numbers is 4. So I'm going to multiply both sides of my equation by 4. And when I do that, the 4 and the 2 would cancel and become 1 over 1 times 2. The 4 and the 4 would cancel and become 1 over 1 times 1. And then the 4 and the 2 would cancel here. So now I have an equation that is much easier to look at. Since this new equation has no coefficient for y, I would solve that one for y to use in substitution. So I would substitute for the y, go ahead and solve that out for my x value. Once I've got my x value, I can plug it back into that substituted equation and get my y value. So substitution in the lab, it will tell you to use substitution or elimination. If you're not comfortable using substitution and you're not having to enter your work, you could always use whatever method works best for you as a learner. If I want to solve two systems by elimination, that's when I'm going to try and have two variables that are going to cancel out when I add them together. So if you look at these two equations, if I imagine adding these two equations together, the negative 2x and the positive 2x would essentially cancel out. And then the 3 and the 2 would add up to be 5y equals negative 5. Now that I only have one variable, I can quickly solve this for y, and I get y is negative 1. So elimination can be a little faster when we can cancel immediately when we're adding the equations together. You're going to follow the same step to find that x coordinate, and then you can plug back in to check your answer, or you can stop there. Now, when you're plugging back in, you can use Web 2.0 to help you, because that fraction 7/2 might be challenging, but you do have the ability to use those calculators to help you out. So I would probably plug 7/2 into the second equation if I was checking my work, because I don't have a negative there. If I want to solve by elimination, it is best done when it's in standard form. So I want the x and the y on the left-hand side of the equal sign if it's not already given that way. If I need to do a transformation so that something cancels out, I would have to take care of that next. Then I would add the two equations together, solve for the variable, and then plug back in to find the other value, ideally stopping to check my work to be sure that my work is correct. So if I wanted to solve this system, this is different, because in this system, when I add these together, I'm not going to have something cancel out automatically. So that's where step 1 is coming into play in that list. So what I can do is I can multiply equation 1 by 7 and equation 2 by 3 to be able to get those y's to cancel. Now, why did I choose to cancel the y values? I chose to cancel the y values because they already have different signs, which just makes the arithmetic a little bit easier. When we multiply every single term by 7 and every single term in the bottom by 3. Then I can actually add them together and I get x equals 5. Once I have that x equals 5, I can plug into one of the equations, and it doesn't have to be the transformed equation. You can go back to the original because my transformed has larger numbers. I plug it in and I get my y value. There are some special systems of equations that you're going to notice as you go through and you're solving the question. So let's just pretend that I don't know this is a special system and I'm just solving it. So what I would do is multiply the top by 4 so that my things would cancel out. So once I have that multiplied by 4, my x's and my y's cancel out, and I just get 0 equals 0. This is a special case of a dependent equation. When you get 0 equals 0, 2 equals 2, 6 equals 6, that's always true no matter what you plug in for the x or y value. In that case, what's actually happening is your lines are graphed one on top of the other. They are multiples of each other. So when that happens, there are an infinite number of solutions, and in the lab, you could choose dependent solution, or you could choose an option that indicates there are an infinite number of solutions. In this one, if I wanted to go ahead and cancel them out, I would multiply equation 1 by negative 2. You could also multiply equation 2 by negative 1, and then no, you have to multiply by negative 2. Once I do that, I have this new equation, and the x's and the y's cancel out on the left, but the right doesn't cancel out. This is called an inconsistent system because that's never true. 0 is never going to be equal to negative 2. So when that happens, the lines are actually going to be parallel, meaning that they'll never intersect and never have an answer. So in special cases, there are infinitely many statements if you get a true statement like 2 equals 2, 1 equals 1. In a special case, if you get something that is false, like 1 equals 3, 2 equals 4, that's going to be no solution in the lab. It's really good for you guys to take a quick graph and Desmos before you even start the question to see if they are parallel to start off with, or if they're the same line to start off with, because that's just going to help you move the homework that much faster. If I want to determine the number of solutions, this is for if you don't have the use of Desmos.com. What I would do here is I would type these both into Desmos.com, and when you type them into Desmos.com, you're going to see they have the same slope and the same y-intercept, so you're going to see just one line come up. It's not a window error if you see one line. That means that there's an infinite number of solutions, and that my system is going to be that indication of an infinite number of solutions within the lab. So you're going to be choosing the infinite number of solutions. I would type this into Desmos. You don't need to move the y's to any side. You can type it in exactly as it is. And if you type this into Desmos, you should see that they have the same slope but different y-intercepts, which means these are also parallel lines and they don't have any solution. So this one over here, it's going to graph the same line, which may look weird in Desmos at first. This one is going to graph two parallel lines, which means no solution.